So next, we have a quick introduction to UT's GeoH2 with Dr. Mark Shuster, research to advance the hydrogen economy at scale.
Great. Thanks, Dave. And good morning, everybody. It is kind of a pleasure to be here. This is a fun conference, you know. Just on the basis certainly for me and my colleagues that I'll introduce a little bit later, you know, we are doing a lot of work in the hydrogen space in our little niche in storage and leakage and looking at emissions. But I do appreciate that, you know, that we're approaching Hydrogen Day, which happens to be my birthday, by the way. And, and it's just kind of fun to see, not only in a group like this, but just more broadly, how much attention, how much work, how much effort is going to hydrogen and trying to get this all sorted out. And, you know, at this point in time, you know, my perspective is I don't think we know, but I think there is enough energy and push that, hydrogen will take hold. And certainly from our perspective and our focus on our work on storage and related aspects, we see that being a significant part of the solution for the future. Just by way of background, so I'm a deputy director here at the Bureau of Economic Geology. I've been at the Bureau since 2016. Before that, I was with Shell for 30 plus years. I retired from Shell. I was working upstream, working in research, doing a bunch of different things. And my involvement in hydrogen goes back to almost 4 years ago, where we started to look at this question of what it would take to effectively scale up hydrogen, you know, assuming it takes hold. And this is where we realize that storage is going to be a significant part of this. Infrastructure will be crucial, and so I wanted to have a look at that, as well as some of the other related aspects, so like in situ generation and some novel concepts. So anyway, what I want to do with my talk is really kind of set the scene for a discussion that we'll have with my colleagues and panelists here. And also, as we do that, address any questions you might have from the audience. We have a few thoughts that we want to share in this context. And so hopefully we'll view this as a kind of an open dialogue and conversation. So Mike Lewis showed a version of this chart earlier. This is taken from the U.S. Department of Energy. But, you know, it's really important to think about hydrogen as a part, not the end solution, but a part of a low-carbon economy. You know, electrification, for lots of good reasons, is important. Hydrogen's role is, and when I talk about hydrogen, I mean low-carbon intensity hydrogen, or clean hydrogen, as it's often called, is, you know, to essentially address parts of, you know, our energy needs that really can't be addressed by electrification. There's a lot of discussion about hard to abate. So when you talk about refining or petrochemical manufacturing, you know, you need a feedstock. And you want to have that feedstock be low carbon. If you're talking about industrial heat, you know, you'd like to have that be low carbon. And that's difficult to do with electrification. So, it has a key role. And the other, I think, compelling component of hydrogen is that it's so versatile. So, you know, you can make it through renewable power or nuclear power or from fossil fuels coupled with carbon capture and storage. You can transport it. It's nice to have molecular fuel, right? And so it's great to be able to do that. You can pipeline it. You can truck it after you liquefy it or compress it. You can turn it into ammonia or other derivative compounds. So, you know, this is really a great attribute of hydrogen. Storable. So we'll talk about the storage. And, you know, we're going to focus predominantly on geological storage in our discussion here. But this provides opportunity for storing a lot of energy. And you'll see, lessons learned from our natural gas system in the U.S. It's fundamentally important for energy systems. It also provides for long-term storage, which is really difficult to get with batteries, right? It's great for diurnal or daily discharge, but not for long-term storage. And I already mentioned the multiple sources. So, we can make hydrogen, low carbon intensity hydrogen, lots of different ways. So, the value chain that, we want to discuss is something shown like here. From feedstocks, so where are you going to get the energy? How are you going to produce the hydrogen? How are you going to transport it? Where does storage interplay? And, how do you effectively connect the supply of hydrogen to the usage or demand of hydrogen? And storage is really fundamental for that. I mean, not just of hydrogen, but any of these value chains, because it provides for ways to manage and buffer intermittency and ensure security of supply. So resiliency and reliability. So let's focus a little bit on geological storage. And what we're talking about is essentially storing large volumes of hydrogen in caverns in salt. These are dissolution caverns that are basically mined out with fresh water, or storing hydrogen in depleted oil and gas fields, or storing hydrogen in saline aquifers, or also in line caverns. You take a cavern, you line it, and make it impermeable, and you can store hydrogen in that. We're going to focus really on those top three in our discussion today. But it's important that we're addressing all these opportunities because the geographic coverage is fundamentally important depending on which of the value chain pathways you're talking about. How do you link supply to demand? And they may be dislocated. So some lessons learned from our U.S. natural gas system. So first point, and being a geologist, I think this is an important one, geology is important. It really informs your options for storage. And when we look at the U.S. Natural gas storage system, there's a lot of gas being stored. We have 400 underground storage sites for natural gas in the U.S. And that has a capacity of over 4 trillion cubic feet of gas, which is about 13% of what we consume on an annual basis. So, it's really providing a resilient and reliable system for moving these molecules, this energy, from point A to point B around the country. So when we think about expansion of a hydrogen economy, and we're not there yet, we've got little bits and pieces of hydrogen supply and utilization. But if we want to expand, we need to be thinking about that network for expansion. And this is where storage comes into this whole view of what sort of infrastructure is going to be required. The point about importance of geological storage options is shown in this chart. So when we look at storing hydrogen in steel containers, these spheres that you see at the NASA sites or whatever, yeah, it's doable, but these are, in relative terms, small capacity storage containers. And they're also costly because, you need high-grade steel for these containers. When you compare that with what you get out of the geological storage options, they really pale in comparison. So a salt cavern, a typical one I'm showing here, you get, 20-fold increase. For a depleted field, a typical one, it's much more than that. So these are important for viewing this expansion of hydrogen economy. And just put this in context also of comparison with batteries. So again, don't get me wrong, electrochemical batteries have their place. They serve a really key role, particularly for daily storage. But they're limited in capacity. They're also limited in terms of the total amount of energy that can be stored. So if you compare, this is the Vistra site, and it used to be the largest battery system in the world. I'm sure there are bigger ones now. I don't know. But you compare that with a small geological storage, which in this case would be about a small salt cavern storage capacity of a BCF or so. That has literally 100 times the amount of energy that can be stored. And the good thing about the salt caverns, or depleted reservoirs, is that you can store this energy, this hydrogen, indefinitely. So it really opens up for managing time shifting, particularly weekly, monthly, seasonal, or just strategic storage. You have it. If you talking about, and Mike was mentioning in his talk, you're generating let's say hydrogen intermittently from wind or solar. You store it up. You can keep it there. You can keep it there when you can use it, or when basically the price of energy can allow you to do a little bit of arbitrage and sell it at a higher price. So it's important to think about this in terms of projected demands. And this is a couple of charts from the Department of Energy's roadmap that was released in final form this year. And so their projection, and nobody has a crystal ball, but it's 50 million metric tons per year by 2050. So, and that's to feed a number of sectors, industrial demand, heavy transportation, and others that are shown here, ammonia, methanol production, et cetera. So, but 50 million metric tons is a lot. We are currently producing about 10 million metric tons of hydrogen today. This is gray. This is not, blue hydrogen, as Mike was alluding to. So it's coming from methane reforming, but without carbon capture and storage. So we basically have to think of, in the next 30 years or so, going from a system of 10 million metric tons of production of gray to now clean production at 50 million metric tons, with this projection. So if the DOE is on target. And we can also compare it with other growth projections put forward. There are a lot out there in the literature. Here it's just for comparison, looking at the DOE, which is that 2050 case that projections noted there. But I'm also including the FCHEA projections of their base and ambitious case for 2050. So that, and to do that really just to provide a range, from 20 to 50 to 63 million metric tons per year. So that's a lot of production, but it's certainly in the context of infrastructure and transport, this equates to over 20 trillion cubic feet of gas. So we have to think how we're going to produce, transport, and deliver that gas, and realizing that some will be produced and used effectively just on site. So you may not need a whole pipeline network for it. But if supply and demand are separated geographically, then we have to think about how we're going to transport. And if we want continuous supply to address intermittencies, then we have to have storage to solve that issue. So anyway, with that context, there's a lot that needs to be done to address, how we're going to scale up storage and how that's going to fit into the hydrogen value chain. Particularly with a focus on, I think, where we see demand developing, which is industry, heavy transportation, and also power. Many technologies are already in use. Salt caverns, one. Mike mentioned, there are 3 facilities in Texas right now that store hydrogen. but at a relatively small scale. And from our perspective, and where our group is focused, is trying to understand some fundamentals of how hydrogen behaves in the subsurface, trying to get at the costs and the efficiency gains, looking at different systems through techno-economic analysis, and also addressing where we see market demand being, and identifying some of the risks in developing mitigations, particularly with leakage. So we formed this consortium called GeoH2. And, a large part of this is focused on geological storage, related techno-economic analysis. We are also looking at some novel concepts like natural hydrogen. Can we go out and explore for it and find it and produce it at an economically viable cost? Can we make hydrogen in situ from oil fields or from non-fossil fuel minerals? There's a process called serpentization. So can we harness that? So we've got many companies as sponsors and other organizations, and they're looking at this in the long term, how to make hydrogen storage, how to make hydrogen economy work at scale. And we've assembled a fantastic team, faculty, researchers, postdocs, students, and you'll see or get to meet a couple of these today. But the key thing for us is trying to have this spread of capability and discipline so that we can tie all these pieces together, because these are complex problems. And in doing so, we've been very active over the last couple of years, generating a lot of publications, getting out there, giving a lot of talks at conferences. We just hosted a Salt Mining Research Institute for a tour at the Pickle campus just yesterday. And the idea is to get these concepts out, get the experimental work, the modeling work done, to try to hook those together in such a way that would be impactful for basically deploying hydrogen at scale. So with that, kind of a long intro, but wanted to essentially kick off the panel session. And we're going to do this with three esteemed panelists. So we'll start off talking about energy and hydrogen storage in a little bit more detail than what I discussed. Dr. Peter Eichhubl will present that. Then we'll go to some more focused discussion about hydrogen storage in Texas. Dr. Lorena Moscardelli will do that. And then, importantly, we need to think about risks. And we're fortunate to have Dr. Tianyi Sun from the Environmental Defense Fund to talk about hydrogen emissions in the context of their impact on global warming. So with that, I'm going to invite Peter up first. We're going to have a series of short presentations. And let me go ahead and introduce Peter. I'm going to take my spot by this first fern here. So Dr. Peter Eichhubl is a senior research scientist at the BEG and co-PI on the GeoH2 Research Consortium. He has a master's degree from the University of Vienna and a PhD from the University of California, Santa Barbara, both in geology. His expertise is in faults, fractures, and fluids in the subsurface with applications to energy resources, carbon sequestration, geothermal systems, and hydrogen storage. He also supervises graduate students in the Geosciences graduate program at UT. So with that, Peter, please.
It is. Yeah. Okay, so you heard that I'm a geologist, geoscientist. My focus will be on that. However, I have 3 slides, only 3 slides. This is just to introduce our panel discussion here. And I start out with the economic aspect, actually, why we need storage. And you may be very familiar with those plots. The first one is this famous, infamous duck curve, which shows demand-supply effects on a daily basis. The second plot on the lower right shows demand excess variable energy generation versus demand if all the energy for California were produced 100% renewables. And what this is, why I put this in here is to emphasize that for hydrogen, there's two aspects that are of significance. Why hydrogen is an energy carrier, which is perhaps most of interest here, but then why hydrogen is an energy storage medium, right? And that's the focus, obviously, for our group here, because we are concerned about subsurface storage. And the argument has been made that with increasing build out of variable energy generation, we need more energy storage, more perhaps than we have today. There's obviously competing technologies out there, depending on the time frame and other economic factors. Natural gas storage, the main technology today for seasonal storage of energy. Line pack, which refers to the natural gas in the pipeline that can be used for short-term demand variations. Pumped hydro with a limited potential for further expansion. We have peaker plants. Mike Lewis in the morning talked about so-called voluntary demand reductions in Texas with crypto mining. But it's obviously not a storage technology. It's just a way of responding to short peaks in demand. And batteries, we already mentioned here. So hydrogen storage can take a place here in addition to what we already do. And the lower right plot here shows where hydrogen could actually be competitive. It is the long-term seasonal storage, perhaps even longer than seasonal. If you think about how we currently respond to multi-year variations in energy supply demand, it is we have a natural petroleum reserve, for instance. Well, if you move away from fossils, then we may have to think about beyond a seasonal cycle. So hydrogen, subsurface storage hydrogen could take this place. It overlaps, as you can see, with pumped hydro. And again, as I mentioned before, there's a limited capacity to expand this. If you go shorter than a week time scale of days, then we have other opportunities as well. And then maybe the hydrogen storage becomes less competitive. Certainly the subsurface storage, where the withdrawal rate may be limited. So then surface tanks may become the preferred option. And then obviously batteries and compressed air and other ways of energy storage would be the choice here. Dr. Shuster already mentioned other advantages of hydrogen. We can take advantage of our existing expertise in storing natural gas in the subsurface. A lot of that translates to hydrogen. How to manage injection and then the production, how to optimize well placement, how to run the infrastructure, dealing with the hazardous aspects of hydrogen versus natural gas. So there's a lot of expertise that can flow into this. A lot of the workforce could be employed in handling hydrogen storage in the subsurface. With distinct differences, though. Hydrogen is not natural gas. It behaves differently. The hazards are different. There are chemical reactions involved, and I'll get to this in a moment. So hydrogen offers certain advantages that, especially for long-term storage. Surface storage of hydrogen versus subsurface storage. As Dr. Schuster already emphasized, the scale is significantly larger for subsurface storage. In essence, it's unlimited. There's sufficient porous space in the subsurface to use. It is more of an economic question than where do you place it, and how do you manage injection production most efficiently. It is actually considered safer to store natural gas in the subsurface than at the surface, and that would also translate to hydrogen. So subsurface storage may be the safest way actually of long-term storage. Now, I guess I'm talking to a fan group here of hydrogen, I presume, otherwise you wouldn't be here. But we should also be aware of the challenges that are out there, and that's part of why we are engaged in research here. As Dr. Shuster already emphasized, subsurface storage is limited by the geology. So the map on the lower right of the United States shows you where we have depleted oil and gas reservoirs in red, where we have saline aquifers in blue that could be used for hydrogen storage, and where we have salt deposits in the subsurface that could be used for creation of salt caverns and then storage of hydrogen in those caverns. And there are large parts of the US that are white, where that is not an option, right? So you obviously have to, you cannot change this. You have to follow the geology here. So, well, lucky situation for Texas, we have all those options here in this state. And maybe hydrogen storage, seasonal storage would be done primarily in the mid-continent and obviously not in California where they don't have this opportunity, right? The other thing here, and again, this goes back to the economics, which is not really my expertise, but the last point I want to emphasize, the way I see this topic of hydrogen storage going, there's a lot of options right now, and it's pretty hard to predict in which direction we'll go. For instance, will we find that salt cavern storage is the better option compared to porous media storage, depleted oil and gas fields? This needs to be figured out, which creates a certain investment risk, right? So if you want to invest in the technology, how do we know in 5 to 10 years that this will be the direction to go? But as Dr. Schuster emphasized, hydrogen has such a vast application field in a mixed energy portfolio that I think we can be fairly confident that overall it may turn out into a low-risk enterprise. That also applies to the research that we conduct, right? Will it be relevant in 5 to 10 years, or will it be this short blip and then we move on? This is all I wanted to say here for the introduction of our panel meeting here.
Thank you, Peter. So we'll move on next to Dr. Lorena Moscardelli, and she's a research scientist and leader of the State of Texas Advanced Resource Recovery Program at BEG. Her experience is in seismic geomorphology and interpretation and geoscience data integration. She received a degree in geological engineering from the Central University of Venezuela, a PhD in geological sciences from the University of Texas at Austin, Hook'em Horns. Prior to her current position at STAR, Dr. Moscardelli was a principal researcher at Equinor. And most recently, she's taken a strong interest in understanding the role of geoscience research as part of the ongoing energy transition while contributing to STAR's main mission of conducting geological research in the increase of production and profitability of energy resources in the state of Texas. So with that, Lorena.
Thank you. Can you all hear me? Yes? Perfect. So I'm curious, how many students do we have in the audience? Don't be shy. How many engineers do we have in the audience? How many geoscientists do we have? Yes, very good. So, well, first, thank you for the invitation, Mark. It's a pleasure to be here. So I have a few slides to share with you. We have been talking about hydrogen. I guess most of the morning we have been thinking about blue and gray hydrogen or green hydrogen and so on. I just want to make you aware that, there are also other types of hydrogen, including natural hydrogen. This is something that is starting to get some traction. Some research groups out there with interest from DOE, actually. ARPA is investing a great deal of money into research into this. And I'm not going to go too much into detail because I don't have time for that. But once again, the role of the subsurface on this, that implies, the exploration for ultramafic rocks that could be generating this kind of natural hydrogen. This is the case on Mali, for instance. There are other concepts that are linked to the geoengineering component of things where you would actually find these ultramafic rocks, inject supercritical CO2 and water and kind of get that reaction going with fracking and so on. So I just wanted to make you aware of this also as one important component of research and something that GeoH2 is also addressing. Mark was talking about the value chain during his presentation. And I think this is extremely important. With all the geoscientists that I work with, especially students or early career people, I think for us as geologists, it's important to have this mind frame in which we think about the whole thing, you know. As geologists, maybe what we're more interested in is storage and subsurface conditions, but it is extremely important if we want to make a difference to see where that fits in the bigger picture of things, right? And this is important because in the cartoon on the left, and I don't think this is working that well, but in the cartoon on the left, we try to capture the level of complexity that you can have in terms of subsurface conditions. Let's think, for instance, in Texas Gulf Coast region, right? We have a lot of salt formations that look like these, salt domes, where we can have our salt caverns. Actually, there are many salt caverns in there storing natural gas and hydrogen. But you also need close proximity to infrastructure, refineries, transportation pipelines, and then natural gas supply. And if we're talking about blue hydrogen, then we need to find places where we can sequester our CO2. All these things have to do with subsurface conditions, okay? But at the same time, as Peter was also mentioning, it's a matter of geography, right? You cannot move a salt dome from one place to another where it's more convenient. So maybe for some parts of the United States, salt is not going to be the solution. Maybe it needs to be porous media, right? So these are things that are important to take into consideration. And again, thinking about the hydrogen value chain, feedstock, we have natural gas with our fields. We have steam methane reformer or autothermal reforming. We need to capture the CO2. We need to sequester the CO2. And then we need pipelines to transport these things. Part of it can go directly to market. Part of it needs to go to storage. Salt domes. We love salt domes. They're fascinating geologic formations. And traditionally, we will have a lot of production in Texas or in the Texas Gulf Coast, oil and gas production that is on the flanks of these salt domes. These salt caverns are inside the salt domes. These salt domes can be as large as Mount Everest. So that gives you an idea of the scale that we're talking about. Each of these salt caverns can be more than 200, 300 meter in diameter, more than 2,000 meter or 2,000 feet in height. So quite big. One salt dome can have up to 40, 60 salt caverns. And then, there is a great deal of complexity within these salt domes. Mark was mentioning that yesterday we were hosting a workshop with the Solution Mining Research Institute, and that crowd is a lot of drilling engineers, mechanical engineers, and so on. And it's really fascinating to hear all the operational complications that they sometimes have on this infrastructure, and to think about how subsurface conditions are controlling some of those problems. How can we predict that? How can we mitigate those problems? How can we optimize the engineering of these things? For hydrogen, this is particularly important because the molecule of hydrogen is a whole lot smaller than the methane molecule or nitrogen. They do a lot of testing with nitrogen. So this is a very interesting component. On the techno-economic side of things, we are working very closely with Ning Lin, actually our chief economist at the Bureau, and our engineers. And we're trying to see, and we have a poster outside on this, where are those domes located geographically? Where is the infrastructure, the pipelines, the refineries? And how we can calculate hydrogen storage capacity, taking into consideration the thermodynamics of hydrogen, right? So it's a fascinating topic. Now, everything is bigger in Texas, of course, and we have all kinds of salt formations, different types of salt formations on the state, and we cannot leave behind the Permian Basin on West Texas. In here, we also have salt formations, but these are different salt formations. They're different in origin, age, and how they look like in the subsurface. This is what we call a bedded salt formation. This configuration is similar to the configuration in Teesside in the United Kingdom, where there is also hydrogen storage. In here, the salt caverns are smaller. There is a great deal of heterogeneity on the subsurface with different types of rocks and minerals. That increases your risk of reactivity for hydrogen and also leakage. So yeah, and then in terms again of the value chain, feedstock, well, the process for natural gas into hydrogen would be similar to what I just talked about for the Gulf Coast. But we also can harness, the renewable potential, both solar and wind, in a scheme in which we can use that renewable power to feed electrolyzers or to power electrolyzers, use water, and then the issue of water quality and so on comes in. And then similar scheme, we can go to market, or we can store that hydrogen at those times of excess renewable generation, and then we can tap into those resources when we need it or when it makes sense. Okay, so there are different schemes depending on where you are and what the subsurface conditions are. Yeah, just a mention here. This is the Mitsubishi, project in Utah. As Peter was mentioning, salt formations are constrained to certain geographic areas, and right now they are constructing these 2 caverns in Utah to store hydrogen. Most recently on the news, Chevron announced, I think they got 25% or something into this project. So this is something that is happening. One thing that I would like to say in here is that when you look in the literature and sometimes you talk to people, you oftentimes hear hydrogen storage is a proven concept. It is a proven concept for the use on refineries and for fertilizers, but it's not a proven concept yet for power generation. And the cycling in terms of storage, the cycling of injection withdrawal cycles here on these caverns is the big challenge and something that we need to understand. So the movies are not going to show up, it doesn't look like, but that's okay. I'm not going to dive too much on this, but essentially I was talking about salt, but as Peter was mentioning, we also need to consider porous media. Porous media has larger volumetric capacity to store hydrogen, and I also should say, salt formations is the things that we can manage in the short, medium term for hydrogen storage, but we would need thousands of salt caverns, and there is not enough salt to get to the storage levels that we would need in 40, 50 years. So we definitely need development of technologies associated with porous media. There is a whole lot more challenges, technical challenges that need to be addressed in there, microbial, interactions, diffusivity issues, and so on. But a lot of active research on that. So this is my final slide, and the reason why I was asking, the audience, how many students, how many engineers, how many geoscientists. We need a lot of human capital to be able to tackle these challenges. And unfortunately, not only in the United States, but in other places, we have seen a decrease in interest on geoscience degrees, and also some aspects of engineering, as petroleum engineering, because traditionally this has been associated with, the oil and gas industry. The expertise of the industry, the oil and gas industry, is transferable to these challenges. And these are the individuals that have the experience to be able to make this happen. So just a word of encouragement to students getting into these fields, that there is a lot of work and challenges that need to be resolved on this. So great. That's it.
Thank you. Okay. Last and certainly not least is Dr. Tianyi Sun. She's a climate scientist at the Environmental Defense Fund, a nonpartisan, nonprofit organization that relies on science and economics to tackle climate change and other pressing environmental issues of our day. Tianyi holds a PhD in climate dynamics from the University of Texas at Austin and did her undergraduate studies in atmospheric sciences at Nanjing University, China. Her work at EDF focuses on the impacts of short-lived climate pollutants such as methane and hydrogen. She explores how their emissions and mitigation affect the climate system, as well as the role of short-lived gases in net zero emission pathways. She also leads EDF's hydrogen science work on hydrogen emission measurements and their climate implications. Thanks, Tianyi.
Thanks, Mark. Realize I didn't make a title slide, so we're just going to dive right in. So I'm a climate scientist, so aside from all of the questions, the geology questions, the technology questions, the economics question we're asking about hydrogen, I'm always stepping back and thinking, what are the factors we need to consider so that we make sure hydrogen does achieve its maximum climate potential? And there are many factors in this, from how it's made, managed, and to how it is used. From how hydrogen is made, if we're thinking we're going to use natural gas with carbon capture to produce hydrogen, then we need to think about the upstream methane leakage associated with and how efficient is carbon capture, how permanent is that storage. And from how hydrogen is used, we need to consider, for example, even though hydrogen is a very versatile molecule and it can be used for almost anything you could imagine in today's economic sectors, but not every use is the best for hydrogen. So for example, heating our homes, it can be done much more efficiently and cheap using electrification rather than using hydrogen. Maybe in some extreme cases when you're dealing with really extreme climate, there is a reason for adopting hydrogen in some way, but it's certainly the exception, not the rule. That's just one of the examples where hydrogen may not be the go-to solution for that particular decarbonization challenge. But today I want to focus a lot more on how hydrogen is managed. So this is about hydrogen molecule itself and how if we can hold on to this molecule while we're either producing it or transporting it or using it, it will cause warming in the climate system. And this is a fairly new concept to a lot of folks that we talk to, and we've, received a lot of blank faces and like jaw-dropping moments if you're talking about hydrogen being a climate pollutant or a greenhouse gas. That's so strange. So we're going to dive into that. But I thought this was very relevant to storage and also how we transport hydrogen. You can imagine to get this very tiny molecule from point A to point B, there are many transfer points along the way. So there are many opportunities where this molecule can slip through. So about how it works in the atmosphere. So hydrogen itself does not absorb any heat. It doesn't absorb infrared radiation. So it's very different from what you would consider a standard or typical greenhouse gas like CO2 or methane. But when it's emitted into the atmosphere, it reacts with the OH radical in the atmosphere. We call OH the atmospheric detergent, and it reacts with many other gases in the atmosphere. And the main one is methane. So when there's more hydrogen in the atmosphere, there's a competition with methane, with the OH radical. So there's less OH radical available for methane, and methane ends up sticking a little bit longer in the atmosphere and can absorb more heat while it's in the atmosphere. Down the chain, this reaction would also give us some tropospheric ozone and stratospheric water vapor. And all of these three things are short-lived greenhouse gases. So while hydrogen itself doesn't absorb heat, the reactions does make it warmer. So we call it hydrogen an indirect greenhouse gas. You can also call it an indirect warming agent, an indirect climate forcer. However you call it, this is the chemical reaction that is responsible for that heat. So this is not new. We've known the chemical reaction since the 1970s, and the quantification of how powerful this could be has been advancing since the early 2000s. I mean, initially we were only looking at the troposphere, and then over time we're also, taking into account the stratosphere. But the most latest science suggests that if we have to use a metric to measure how powerful hydrogen is as an indirect warming agent, then its power over 20 years is about 37 times more powerful than CO2 pound for pound of equal mass. And its warming power over 100 years is weaker. It's about 11 point, I think that's 6, so about 12 or so over the long term. And you notice it's much more powerful in the near term compared to in the long term, and that's because hydrogen doesn't stay very long in the atmosphere. That reaction also removes it. So itself only stays in the atmosphere for 1 to 3 years. But because methane is slightly longer lasting, so this indirect warming effect actually does last over a decade of time. So knowing how this is it could be a pretty powerful warming impact, we asked the question, so how much of a problem this could cause if we lose a lot of this molecule? And this is the research we published last year, and it's a quite simple, generic, I think, thought exercise, you call it. So we're thinking, if we deploy 1 kilogram of hydrogen every year, and that could be the quote-unquote blue natural gas with CCS, or 1 kilogram of green hydrogen electrolysis renewables, and that should help us avoid about 11 kilograms of CO2 emissions from the fossil fuel that it's replacing. And in this scenario, we consider if we're doing the blue way, then we're considering 1 to 3% of methane emissions associated with, and then 1 to 10% of hydrogen associated with it. Those are just assumptions. The methane numbers are somewhat informed. The hydrogen numbers are very hypothetical. And then consider green hydrogen, we're assuming 1 to 10% of hydrogen emissions. And we ask the question, how much does these emissions matter to the climate benefit of hydrogen we wanted to achieve? So that's shown on the right-hand side. That is a ratio between the climate impact of a hydrogen technology versus climate impact of the fossil fuel that it's replacing. So you see there is a middle line called same climate impact, same impact. That is where the two things break even. So when you switch from fossil fuel to hydrogen, you have no change in climate impact at all if you're at that line. Everything above that line means hydrogen is worse for the climate. Everything below, hydrogen is better for the climate. So you see just from the scheme, in most cases, hydrogen would be better for the climate. So that's the climate benefit that we wanted to achieve. But looking closely, you also see that this bar is very tall. So bottom of these bars are best case scenarios when we only lose 1% of hydrogen, has 1% methane emissions. Top is worst case scenarios. So if you stare at the blue bar on the left-hand side, you see if both hydrogen emissions and methane emissions are high, it can actually be worse for the climate in the near term. But that story changes in the long term on the right-hand side. And that's because both methane and hydrogen are short-lived, so they're more powerful in the near term. And this similarly with the green bar too, even though it's less taller than the blue bar, but that 10% of hydrogen emissions still makes quite a bit of difference. It's a difference between we're achieving 65% of climate benefit or 90, even 95% of climate benefit. So as the emission rate increases, you really do see a significant impact of the hydrogen emissions themselves. So you might be asking, well, 1 to 10 is a very dramatic range, and 10% sounds quite unrealistic. And we really dug up and down the literature and tried to find a more solid evidence to support either a tighter range or a specific leak rate or emission rate that is more realistic, but we couldn't find any. We did end up writing a literature review sort of paper on where are the data sitting today. So on the right-hand side, you see this lots of scatters on each segment of the value chain in today's hydrogen value chain, and some of them are also relevant for the future hydrogen value chain, if not all of them. And you see these scattered dots that goes across the y-axis from very close to 0% emissions all the way to 20% emissions. And if you look at the legend, you will notice that these are assumptions, calculations, lab experiments, and model or simulation. There are just no empirical measurement data that's supporting these very scattered dots, and that's probably also why these data are also so scattered. So noticing this, we realize this is a critical data gap that we need to solve for in order to narrow down that range and start to think about the solutions of minimizing hydrogen emissions so we can maximize its climate benefit. We know these emissions can be either unintentionally leaked just through joints and nooks and crannies, but it can also be intentionally released, which I found out a couple years ago, and it was a surprise to me, but maybe it's very intuitive for all of y'all who are very familiar with the engineering. Because we need to, for example, keep a tank at a certain pressure, if it's overpressurized, then you have to vent some of that hydrogen into the atmosphere. And there are purging also in the electrolysis process, purging in the fuel cell process. A lot of that is for safety purposes, and you kind of have to do. So our next question is, how much is it really putting into the atmosphere, and how can we then start thinking about minimizing it? And I highlighted here the very stark, I think, data poor area for salt caverns and geological storage, because that's the panel that we're talking about here today. You see there are only 2 dots there. They're quite close to each other, so maybe it's hard to see. But for salt caverns, there are only 2 data points that are a model simulation, and for depleted oil and gas field, there's just no data at all. So there's quite a bit of research, even from the theoretical side, to explore what would be the estimate, and of course from the measurement side to explore what exactly is the emissions coming off of these systems. So addressing this huge data gap is my responsibility day to day. So if you're curious what we are doing to try to fill this gap, then I'm happy to talk about it afterwards. That's what I wanted to share. Thank you.
Thank you very much. I realize that the intent of this session is to have a panel, but we've been kind of talking one way, and whilst we were thinking of kind of starting with some questions internally, I think we'll change gears and just open it up for questions from the audience right now. And if there aren't any, we've got some thoughts and some questions that should be asked. So let's open it up for questions, please.
Great panel, guys. So what's the storage efficiency of hydrogen when you store it in salt caverns? How much can you get it back over a period of time?
Yeah.
Sorry, what was it?
Lorena,
What
you
was
want
the question?
the storage efficiency in salt caverns?
Well, I guess it depends on how you define efficiency. One of the advantages is the volume, right? That it allows you to store huge amounts of hydrogen that can, help us then with seasonal, constraints. The other thing, especially for salt caverns, is it's like a tank. It behaves like a tank, and then the injection withdrawal cycles can happen very fast, with some constraints linked to, subsurface conditions and creep and so on that will affect the lifespan of the cavern. But I think in terms of salt caverns, those are the 2 main advantages.
And I'll just add to that. So, when you're talking about gas storage, there are a couple of terms. One is working gas and cushion gas, right? So working gas is that gas that you're going to be turning over. And then there's the cushion gas, which is effectively the gas there that's remaining to maintain pressure in the reservoir that, eventually could get produced if you need it, but you'd be reducing the reservoir pressure. So in a typical salt cavern, it's about, the cushion gas is about a third, 33% or so. So the working gas is about 2/3 of the volume. But it depends. I mean, you can produce that back eventually, but then you're depleting the pressures.
Next question.
Just to follow up on that question, actually, last night I was reading through this week's issue of Science Magazine, and there was an article about storing hydrogen using metal hydrides, which is nothing particularly exciting. But the thing that really grabbed my interest is their justification for doing so was the fact that underground storage of hydrogen is questionable due to microbe interaction. And I had never heard that before. Is microbe interaction such a significant problem that it may make underground storage of hydrogen impossible?
Peter, you want to field that one?
So it is a concern. And one reaction is to turn the hydrogen in the presence of any carbon compound into methane. And the irony is the one operational porous media storage for hydrogen was conducted over the last few years in Austria, and they actually targeted methane generation in the subsurface. So they produced hydrogen, injected it as a mixture into the subsurface, and were aiming to produce methane, which from a European perspective, right now, maybe that's the objective there. But yes, it is a concern. You want to minimize microbial interactions, and one pathway would be to go to deeper reservoirs that are high in temperature that would minimize the microbial activity. It is obviously also microbes are a concern in subsurface oil and gas as well, and then they use a microbicide. But I'm not sure if this is the way we want to go with hydrogen. But yes, it is a concern. It's part of active research. What are the reaction pathways? It's complicated. You may bring in microbes by the operation itself, so there's a contamination concern. They may be present naturally. They may depend on how much other metabolic, and I'm not a microbiologist, but other metabolic compounds are there already for them to interact with. So it's also dependent on the reservoir rock type to a certain extent. So there are many factors involved. And that's part of open research. I think it's manageable if you go deep enough, the temperatures are high enough, but then it may become a cost issue as well, right? Because then your compression costs are getting higher.
I just add, salt caverns seem to be a little bit different because the microbial communities don't like the salty conditions as much. So that's what I've gathered from going through the literature. That so that's kind of limiting, at least for salty storage.
Thank you very much for the talks. So speaking of subsurface salt cavern storage, so my company has some idle Gulf of Mexico natural gas pipelines offshore and onshore facilities that are nearby a lot of the hydrogen activities onshore. And I was looking for a map of the relevant salt caverns and other things to see if there was a tie to the infrastructure for that. So is there anywhere you could point me to on that? Is there...
Yeah, there are published sources of salt cavern locations on the United States and in Europe. And I think the main source for that would be the Solution Mining Research Institute library. But we also can have a conversation afterwards, and I can, point
Thank you very
you
much.
to that. Yeah.
Hi, thank you so much. First off, sorry to my Texas people, go Gauchos, UCSB, love it. But regarding salt bed caverns, we're looking in the area of Kansas. I'm just wondering to my scientist friends, what are the technical limitations to doing, technical and actually political limitations to doing salt bed hydrogen storage, even though it's been proven in Europe? I wonder what those limitations are, first. And then second, are you aware of any commercial developers looking at making salt bed storage for hydrogen happen in the U.S.?
I'll go with the technical part. The main difference, well, there are several differences, but one of the most relevant ones in terms of salt caverns in embedded salt versus domal is the size of the caverns. So I know, for instance, in West Texas, I think the maximum thickness or the minimum thickness that you need on your salt or interval has to be 380 feet, which means that your salt cavern will be, because you need a little bit of buffer in there, is going to be a little bit smaller than that. That compared to salt caverns in the Gulf Coast region, where we're talking about 2,000 feet high versus, and I don't know, 200, 300 feet in diameter. So the first constraint is these are going to be smaller caverns. It's the case also on T side with hydrogen. That said, that's not something that would prevent development of these projects. In West Texas and also in Kansas and many other places, there are salt caverns in embedded salt for natural gas storage, for propane, butane. They store all kind of things in there, so that's not a limitation. Your second question was?
Are there any commercial developers actively exploring embedded salt development?
There are many.
In the Midwest?
There are many that I can think of, yes. There is a lot of interest. Now, we're talking about hydrogen, that's the topic. But one of the things that I'm also interested on this, we're talking about energy storage in general, which has a connection to energy security, So a lot of these developments are not only into thinking about hydrogen storage, but also thinking about expanding, natural gas storage capacities. I know SPR, the Strategic Petroleum Reserve, is actually right now doing some work in 2 facilities to revamp infrastructure and put things in order. That they have withdrawn from those facilities often lately. So I think the topic is broader than hydrogen storage, is energy storage in general. Yeah.
Got a question over here.
So this is for the most recent presentation on emissions. There's a slide that mentioned there's about 11 kilograms of CO2 avoided in the fossil fuel industry per kilogram of hydrogen deployed. Is that solely accounting for production, and how is that value calculated?
So that is very much an average number for, I think, the life cycle impact. So it's not just production. So how it's calculated is actually from a Hydrogen Council report in 2021. I think they projected that by 2050, globally, we're going to produce 550 million tons of hydrogen, and that helps us avoid 6 gigatons of CO2. So that average number is actually taken from that report. If you consider different use cases, this number would definitely vary. For example, I think just from the generic sense, if we're using it to replace gray hydrogen, I think that number would be higher. And if we're using it to combust and produce power, then that number might be similar or lower. So it really depends on what use case you're considering. But overall, on average, across different sectors, that's pretty much the general magnitude.
Hi.
Hey, Brian.
Hey, Mark. First of all, thanks so much for the presentation and the great work that BEG is doing on underground hydrogen storage. In many ways, I think underground storage is sort of the last frontier for a robust nationwide hydrogen infrastructure. Having said that, salt domes are great. I wish they were everywhere, but they're not. And for us to have this nationwide infrastructure, I think it strikes me that we're going to have to really sort of crack the nut and solve the issue on depleted reservoir storage, whether it's aquifer or production storage. Has BEG looked at? You've identified the porosity issues, the leakage issues. You've talked about some of the underground chemistry, but I haven't really seen a lot on the economics that would drive underground storage. And for cushion gas, for example, you talked about a minute ago, that requires a lot of hydrogen for most depleted reservoirs for that cushion gas. What are the economics that would drive that? What are the threshold that we have to hit to make this not only a technically viable option, but an economically viable option?
Yeah,
be interested to hear your comments.
Yeah, Brian, thanks. And maybe I'll also let Lorena and Peter speak to this. The first answer is I wish Ning Lin, our economist, were on the stage because she could give you specific numbers. I can't off the top of my head. But definitely we're addressing this because part of the reason that we want to have this integrated team is to be able to come up with robust costs to be able to assess the various value chain pathways and where storage would fit into this. Because there are a lot of costs associated with hydrogen storage in the subsurface. There's processing, you got to purify the water, the compression is a big element of cost. But when you look at the various pathways that we've looked at, and including some work, like sourcing hydrogen in West Texas for potential markets in the Houston area, it looks like it could be competitive. And that's even thinking about additional transportation costs and the cost of building these storage facilities. So, and I say that because that's in comparison, with these above ground containers, and they're just expensive. And if you're talking about a scaled up system, you would need a lot of those. So the alternatives are more costly is maybe the simplest answer.
Let me add to this. A big part of the answer is the engineering side. How do you do that, actually? How do you inject and produce? And we're working with Professor Delshad on this topic, and you have some fantastic posters outside, right next to the coffee stand, that tell you, for instance, how different types of cushion gas affect how much of the stored hydrogen you can reproduce. So it matters, the detail matters to a large extent. How many wells, how many injection production wells do you have? How do you handle the pressure in the reservoir? How do you handle water production to keep the pressure under control in the reservoir? All that matters greatly, and that is obviously ongoing work in our group on the reservoir engineering side. And I think there will also be presentations in the late afternoon that address this. So I'm not sure if you're there yet to give you a proper answer to this. We can work with the numbers we know right now, but I think this is really in flux, trying to figure out how to do this most economically.
Yeah, and one additional point, Brian, which may be of interest to you and GTI and other companies. So we've actually developed an application, a software application, to allow us to do the net present value modeling with what we think are as robust assumptions as available right now to cost out the various options.
Hi, I was curious about these, if there's competing use cases for these depleted oil fields and salt domes that would impact using hydrogen. I guess the appetite for oil and gas companies to consider using depleted oil fields, I guess, are there any competing use cases out there that could impact using hydrogen?
I'm happy to start with an answer
Go
here.
for it. Yeah.
So, obviously, it's also just not for storage, but the switching costs. People have been talking about like repurposing natural gas pipelines for hydrogen. There are some technical issues that go along with that, but it's also, those pipelines are transporting natural gas for a reason because they're getting the supply to a buyer, right? So there are storage, current natural gas storage facilities that could be repurposed for hydrogen, but it really is going to come down to the individual company and that individual facility is a choice they want to make because there's going to be a cost associated with it, for sure.
No, and it's the market, right? The market is going to be the incentive, and I guess that's the question for me. This is not cheap, obviously. It's risky, and the initial capital investment for these things is huge. And therefore, with anything in technology, the first ones to go in are the ones that are taking the greatest risk and developing the technology, and the ones that go be people waiting, right? You go first and do this, and we'll see what happens. But I think going back to the value chain component of things, once companies of all sizes see that the market is ready to pay what it costs to be green, it will happen. And I think it's also a matter of what is the end consumer willing to pay? What are we willing to pay for this to happen? So I think that's part of a broader, conversation that might be a little bit more challenging. Yeah.
Question over there.
So on the topic of salt cavern integrity, how important, what's the relative importance of the amplitude of cycling versus the frequency? Just thinking in context of, we've been operating salt domes for a very long time for fertilizer production and for oil refining, but then with green hydrogen production and power utilization, you're having potentially a much higher frequency of cycling, but at a lower depth of discharge.
Yeah, I mean that's going deep into the technical component of things, but you are completely right. The cycling is, and that's why when I start to learn more about these things, this phrase hydrogen storage and salt caverns is a proven concept. It's a proven concept right now for strategic purposes. So the injection and withdrawal on these facilities, existing facilities, it might be one a year, one every 5 years. I mean, we don't really have the data. They're very good guarding their data. But in this case, we're talking about cycles that are going to be daily or weekly or monthly. How's that going to look? And these changes in temperature and pressure are not trivial, And then the salt is like toothpaste to a certain extent, and there is a lot of natural creep on these caverns, So over the life of these caverns, they shrink. And depending on the amount of cycling that you have on those, it will affect, the size of the cavern. And there can be also integrity components because you also have your pipes, the cement, and all these things. So these are all active, lines of research. But you're absolutely right. We're trying to understand that better. Peter.
So this issue is the same for natural gas storage, and that, as you have seen on one of the maps that Dr. Shuster showed, there's ample of natural gas storage in salt domes currently being conducted for decades now. As long as it's the issue of fatigue by cycling, as long as you stay within the limit, you can control it. If you go over that limit, then eventually you may get a failure, right? So it is managed. Same for porous media storage, by the way. Same thing, same concern. Is the cyclic load, does it over time lead to failure or not, right? And as long as you stay in that limit, it should not be the case. The one difference, though, is that hydrogen could be more reactive than natural gas. Reactive with the rock or the cement. And there could be chemical effects that could lead to a delayed failure response. And that is something that we don't really know too well, because that's unique to hydrogen. That would not occur with natural gas.
And it's a smaller molecule, right?
And then it's more leak prone overall, yeah. But so there's this one aspect is the reactivity of hydrogen that may then, in conjunction with that cyclic load, may lead to failure. That is something that needs to be worked on. I don't think it's a big issue, but it's definitely something to be aware of, especially for the cement that is used for the casing of the wellbore. The wellbore where you inject and produce is probably the weak spot overall.
I think it's a big issue because we have not done it before, So the proof of concept there, that's why the piloting, we're using nitrogen now to test these things. But I think that the main challenge is you cannot trivialize it because we have not done it before. And that's where the work needs to be done.
We're a little bit over, but is there any more? Okay.
Yeah.
So
2 more questions?
2 more questions?
2 more.
Okay.
Actually, this is specifically for Lynn. I would like to know what your organization does to educate public for hydrogen. And if there are any activities, because we really need to be careful about that, because if somebody is going to have their leases in the house next to the porous space, they're going to be very concerned about hydrogen storage. It doesn't matter if it's a salt or depleted oil and gas reservoir. And we've done quite a bit of public awareness, starting from high school students, to the high school teacher for CO2 storage about 10, 15 years ago. And you'd be surprised the kind of reaction they have and the kind of questions and fear they have. And I really think this is part of this whole hydrogen, economy that we need to educate public.
Yeah, thanks for that question/comment. We're doing a lot, but I take it from you that we probably should be doing more and perhaps target a wider audience. I think our main audience are policymakers, industry, and also some community groups that need to know about the risks of hydrogen. I have not personally communicated to high school students. We've done some university outreach like this one. But I can share with you our hydrogen website that has a lot of the resources we have, and then we can certainly chat more about reach a wider audience about these risks on hydrogen. Thanks for that.
Got a question over there, Bob?
Okay, one last following up on the letter. I keep following up on questions. Given that the federal government is now investing millions into trying to understand how much natural hydrogen is produced, how confident are we know what the natural emission rate is?
We're not very confident on the natural emission rate. That's actually one of the bigger uncertainties. I think when I show the global warming potential metric, there is 37 and then plus minus 12, if I remember it correctly. So there is an uncertainty range attached to it, and a lot of it is coming from the lack of understanding on the natural budget of hydrogen. So how much soil absorbs hydrogen, how much natural geological storage of hydrogen, not the storage that we do, but natural storage emit hydrogen. So there is quite a bit of research to be done. And I think a lot of that lack of research was perhaps driven by we weren't really paying attention to this molecule before. We were using it as a specialty chemical, and we weren't, imagining what we imagine today. There's going to be a 5-fold increase in hydrogen production and use for so many economic sectors. So that investment in the future of using hydrogen start to stimulate a lot more research, I think, in this area too. So I'm hopeful that in the next few years we'll see a lot more data and research coming in to solve that natural hydrogen emission question as well.
Yeah, need some funding.
Any more questions? Well, join me in thanking our excellent panel, Mark, Peter, Lorena, Jan.